Welcome everyone to Lecture 5 for Chemistry 141. So today we're going to learn a little bit about the language of atoms and some of the values that we're looking at when we're talking about atoms. In the previous lecture we learned about atomic number, which of course we now know means the number of protons present in the nucleus of an atom. And another similar sounding term that we have is called the mass number. And we saw that atomic number is denoted as Z, and mass number is very frequently referred to as A. And the mass number is the number of protons plus the number of neutrons. So it's really the total number of particles present in the nucleus of that atom. So we can say that A is equal to the number of protons plus the number of neutrons. So number of P plus number of N. And when we have our atomic number and our mass number, we can figure out which element we have as well as which isotope we have. So we can write a full atomic symbol for that isotope, which actually gives us quite a bit of information about that atom. And so here we see our symbol there. We've got our regular elemental symbol there shown as X. We've got our mass number up top, and kind of a reverse superscript there on the left hand side, so that's our mass number, and then the atomic number written down below with Z, so that tells us number of protons. We don't always see the number of protons written there. Sometimes you just see the mass number and the chemical symbol. Once you know the chemical symbol, the atomic number is a little bit redundant, and sometimes you see it and sometimes you don't. Now, when we're looking at isotopes, we generally refer to different isotopes by both the symbol and the mass number. So we give our X, which is our elemental symbol, and then a dash, and then the value for the mass number. So as an example for that, you've heard me talk about carbon-12 in class, and so we would write that as C-12, which again we read or say as carbon-12. If you had a C-13, that would be carbon-13, etc. So here are just some examples here, different ways of writing our isotopes and some of their properties there. These are three different isotopes of neon, and we see that they're all neon, we're all Ne. We notice that they all have the exact same number of protons in the atomic symbol 10 there. And that's the same as the 10s that we see right here. The number of neutrons is different. We have 10 in neon 20, 11 in neon 21, and 12 in neon 22. And those sums, of course, if we say plus, plus, and plus, we get 10 plus 10 is 20, 10 plus 11 is 21, and 10 plus 12 is 22. And so we see that's where we get our different isotope values there. So neon 20, neon 21, neon 22. Notice also that one of them is in much more natural abundance. That's our neon 20 here. That's pretty common with most elements, is that one of the isotopes is present in nature at a much greater rate than the other isotopes. Not all elements are like that, but most of them do follow that trend. So we haven't used the terms ions. It may have slipped out once in a while in our previous lectures, and we haven't really talked about what they are. But ions and atoms are similar, however they are different. Okay, so an ion was an atom at one point, and then it has obtained a charge somehow, and that charge is either a positive charge or a negative charge. Now, if we look at the different charged particles on an atom, we have both protons and neutrons. So you could either gain or lose a proton, or gain or lose electrons. And it really doesn't make sense to gain or lose protons, because then all of a sudden our elements change. It's also very difficult to pull protons off or put them onto the nucleus of an atom. And so instead, the way ions are formed is by the loss or gain of electrons. So that's the only way our ions are going to be formed in this class, is by the loss or gain of electrons. Now, anytime electrons are lost, then you have more positive charges in the protons than you have in the electrons, and you end up with a positively charged ion. We call that a cation. And if you gain electrons, well, now you have more electrons than protons, and you end up with a net negative charge on that ion. And so we call those negative ions anions. So just some examples here. Lithium is an example of an element that tends to lose an electron. So if we wrote like a chemical reaction there, we'd show lithium turning into lithium plus an electron. So we have a balance in charge there. So we now have a lithium plus. Notice that we've written our little plus sign up here to indicate that we have a positive charge. And then we also have chlorine. Chlorine is an element that tends to gain electrons, and when it does so, it forms a an anion there, and we indicate its negative charge right there. Now, why do they do that? Well, it has to do with stability, and the atoms there, lithium and chlorine as atoms, are less stable than their ions are. So lithium plus ion is more stable than a lithium atom, and chloride minus ion is more stable than the chlorine atom. Now here's another term that we want to use when we're talking about atoms or ions. We're looking at back at isotopes here. When we look at the periodic table, we see that we have atomic masses with several digits on there. And how do we report the mass of an element if you have several different isotopes present, and all those isotopes have different masses? And so what we use to get the atomic mass is a weighted average of all the naturally occurring isotopes. And so a weighted average is something that takes into account the percentage present of each of the different isotopes. Chlorine is a pretty good example of how we calculate atomic mass that we see on the periodic table. So chlorine has two naturally occurring isotopes, chlorine 35 and chlorine 37. And we see chlorine 35 is present in quite a bit more percentage than chlorine 37. But we still have to take into account that heavier chlorine 37 because it makes up almost 25% of all naturally occurring chlorine. So this is the way we would do it. We convert our percentages into a fraction and then multiply that fraction by the atomic mass of that particular isotope. So chlorine 35 has an atomic mass of 34.97 AMUs, and we take that 75.77%, turn that into a fraction, 0.7577, and then we add the 0.2423 from the chlorine 37 and its mass in AMUs, and we calculate that all out, and we end up with an average mass of 35.45 AMUs. And if you look at the periodic table, the atomic mass is reported right below the elemental symbol, and it'll be 35.45. So we can express this process just as a simple equation. So we can say that the atomic mass is equal to the sum of the fraction of an isotope times the mass of the isotope. And the n there indicates that we're going to use all of the different naturally occurring isotopes. So we have the fraction of isotope 1 times mass of isotope 1 plus fraction of isotope 2 times mass of isotope 2, etc., so forth. All right, well, let's talk a little bit about moles here. So anytime we're talking about atoms and reactions, a lot of times we use this term moles. It's actually a unit. And what the unit of a mole does is it helps us count very large numbers of items with a little bit smaller numbers. So a lot of times we just call that a chemist's dozen. So in the same way that 12 donuts is equal to a dozen donuts, a mole of donuts would be 6.022 times 10 to the 23rd donuts. So it's the same concept as a dozen. It's just a lot bigger number. So it's at 6.022, and then it's going to have a lot of zeros that come after that. So a mole of anything is just a really, really big number, but it's no different than the concept of a dozen. If we see a dozen, we know it means 12 of those things. If we say a mole of those things, it means 6.022 times 10 to the 23rd. And where we get this number from is it's equal to the number of carbon-12 atoms present in that exact 12 grams of the isotope carbon-12. So how big is that value really? And this is something that we'll explore in class. I don't want to spoil any of the fun here, so I'm not going to discuss any of these in detail in the lecture capture. But we'll talk about a mole of M&Ms, a mole of donuts, a mole of basketballs, and who wants to be a millionaire? So how do we use this concept of moles? Well, what they really allow us to do is to more or less count the number of atoms and molecules through finding the mass of a sample. And if we have that 6.02 times 10 to the 23rd of anything, we have a mole of that material. But the real question is, what's the mass of a mole of something, whatever that something happens to be? And in a way, that's just like asking, well, how much does a dozen of something weigh? And you can't answer that question. It depends on what that something is. A dozen grapes weighs different than a dozen watermelons. Even though you have the same number of those two fruits, obviously each piece of fruit is very different in size between a grape and a watermelon. So atoms are no different. Our different atoms of the different elements have different masses. And so a mole of each element is going to weigh a different amount. So what we really need to be able to do is we want to be able to convert between mass and amount. Now as we start to get into reactions later in the course, we write our reactions, and when we're writing them, they actually can be expressed in terms of either atoms or molecules reacting, or we can think of these in terms of moles reacting. And so we can get these numbers from the number of moles that we have in our reaction. The reason we can do that is because an element's mass of 1 mole of that material in grams, so if we want to express an element's mass in grams, then 1 mole of that material has a mass equal to 1 atom's mass of that element in AMUs. So we can get that information from the periodic table. We saw that 1 atom of carbon-12 weighs 12 AMUs, and what that would mean is that 1 mole of carbon-12 would weigh exactly 12 grams. Okay, so let's take a look at the periodic table at some of our elements here. So we will look at copper, we'll look at aluminum, and we'll look at helium. And again, we'll cover these through in class. So we can use molar mass as a conversion factor, and it helps us convert between the number of grams of material and the number of moles of a material. So here's an example that we'll try to work out in class. We want to know the number of moles of copper in a 35.8 gram copper sheet. And here's another example we'll try to get to in class here. We want to find the mass in grams of 0.473 moles of titanium. So here we know the number of moles of titanium, and we want to figure out how many grams that's going to weigh. Well, that finishes out our lecture 5. Starting to get into a little bit more quantitative material, starting to get into some calculations. If any of those are giving you any problems or any of the concepts that we talked about today, if any of those are confusing to you, please make sure to contact one of us.